Hello, class. This could be the recorded lecture for section 2.4, which is graphing of the other trig functions, tan, cotangent, secant, and cosecant. None of them are anywhere near as important as the sine and cosine, because those occur in real world applications. These are more math stuff, but they're very interesting. So we'll walk through the process and the ideas on how to recognize these graphs and how they behave. And we're first going to start with the tangent graph, which is the third most important of any of the trig functions besides sine and cosine. And remember that tangent of any angle, let's call it theta, is defined as sine of theta over cosine of theta. And the one thing that we want to talk about is we cannot divide by zero, right? Dividing by zero is bad. And so when we talked about calculation of tangent, we had these undefined points, which occurred when the cosine of the angle equals zero. And where did that occur? Well, that occurred at cosine of pi over 2 or 90 degrees is 0. And then cosine of 3 pi over 2 or 270 degrees was 0, and so on and so forth. And you can go the negative side, which would be minus pi over 2, etc., as well. So those were the two undefined points. And when you do the graph, what do we do with the undefined points? Well, when we talked about graphing of rational functions, where there was x's in the denominator, and we had these things called vertical asymptotes. Same thing happens here, as wherever these functions are undefined, we have something in our graph called a vertical asymptote where the graph cannot cross that vertical asymptote. So the way we think about this is that when you want to sketch the tangent graph, and again, I'm not going to really focus on this too much in our class aspect of it. The first thing you want to think about is where are the points that are undefined? Well, we have an undefined point at pi over 2. We have an undefined point at 3 pi over 2. And watch if we go the other way. What I mean the other way is if we go negative, be minus pi over 2, and minus 3 pi over 2. Remember, what do these angles, negative and positive, mean? Around the unit circle, positive is counterclockwise, and around the unit circle, clockwise is negative. Okay, so the next thing is, what is the value of the tangent at 0, right? So if we look at this, and this is our theta, so call it x, right? And this would be the output y. Where is our 0 point? Well, that occurs when sine equals 0, right? So when sine is 0, that occurs at what point? Theta equals 0, theta equals pi, theta equals minus pi if we look at our graph. So if we put those right here, that would be minus pi, that would be pi. You would see that we'd have a 0 point here, 0 point here, and a 0 point here. So then what happens with the rest of the graph? Well, you can get out your old trusty tables or get out a calculator and start plugging a few numbers in. And this is what you would see. You would see that as the values of tangent get closer and closer to pi over 2 or 90 degrees, they start blowing up in the positive direction. And the same thing if you go the other way, they start blowing up in the negative direction towards minus pi over 2 or minus 90 degrees. So when you take a look at the sketches of these graphs, it would look something like that. And again, they repeat themselves over and over and over again. And the idea is that as you move to the right, the units are increasing. And then when you move to the left, you can see that it's going down to minus infinity towards the minus pi over 2, minus 3 pi over 2, etc. And so one of the other things is that you see that this has a period, right? It repeats itself over and over again. But what is the period? Well, the period in this case is different than sine and cosine. The period is here, right? As you can see, it repeats itself over and over again. And what's this distance? That distance is pi. So the period of both cotangent and tangent are pi, which is definitely different than sine and cosine and all the other ones. So to give you a nice pretty view of this graph, it would look like this. There you go. Nice computer generated. Again, these are uploaded. And you can see what we have here is the asymptotes in blue, and dotted lines indicate the asymptotes. And then in red is the graphs. And they repeat over and over again with a period of pi. Really, really important. So you remember when we were discussing cosine and sine, we had 3 attributes that we were dealing with. Number 1 was the amplitude. Number 2 was the period. And we've talked about that already. And number 3 was the phase shift. That's kind of where everything starts. And so you could see that this graph blows up to both positive infinity and negative infinity. And so amplitude really doesn't have a real meaning in this graph. Reason being is that if you multiply tan by a number, it's just going, the number greater than 1, just going to grow faster, right? But it's still going to each infinities. And if you multiply it by a number less than 1 or between 0 and 1, it would also just grow slower. So we really don't talk about amplitude and any of the other trig functions except sine and cosine. But we do talk about period, and we do talk about phase shift. And the phase shift will do 2 things. It moves the starting point. What do I mean by the starting point? Well, in this case, it would be right here at the origin. And it would also going to move the asymptotes. And so when we talked about, let me clear this up here. So when we talked about sine and cosine, we had this standard form, right? We had this A, and then we had tangent of K, and then it was X minus B, where this was the amplitude, but we're not going to worry about that in the rest of these, but we are going to worry about the period. And the period is defined with tangent and cotangent as pi divided by K. And the phase shift will be equal to B. So what happens when we kind of maneuver all these? Well, let me walk you through an example. So in the red one, we'll call this one tan of X. And when we did that one, and let's just do 1 period in this case, it looked like this. So we had this was minus pi over 2, and this was pi over 2. And it look like that. So in this case, our k equals 1. So our period is pi divided by 1, which is pi. And what's our b? B equals 0, right? And so we have no phase shift in this case. So what happens if we do this? What happens if we take the function, let's do this one in blue, and we decide to move it to y equals tan of 2x? Well, basically what we're doing now is we still have a b of 0, right? And we'll do a phase shift in a minute. So what happens when we change the period? So the period is now pi divided by k, which is pi over 2. So basically, what did we do to the period? We cut the period in half. So guess what we do to the two asymptotes? Well, basically what we do to the two asymptotes now is change the asymptotes and cutting them in half as well. So you would see that the asymptote in this case for the blue one would be at pi over 4. And the asymptotes of this blue one here would be pi over 4. And so if you drew this one, it would look something like that. So basically, when you cut the period in half, you move the asymptotes in closer, and because things have to occur quicker, right? Or more often is a better way of putting it. So that's what happens to the asymptotes when we do something like that. So then what happens if we, let's do this one in green. What happens if we do this? Y equals tan of 2, and then we do, need some more room here. So let me erase this blue stuff here, and let me write this right here. So y equals tan of 2, and then we go x minus, let's do pi over 8. So now what do we have? We have the period is still pi over 2, and now our phase shift is pi over 8. So what does the phase shift do? Well, the phase shift moves everything by that amount. So in this case, it's a positive move. So we're moving everything to the right, pi over 8. So what do we move? We move everything. The whole graph moves. And so this might get a little weird looking, but hopefully the colors are going to help a little bit. And so if we move it pi over 8, the 0 point now, instead of being at 0, is pi over 8. See how that works? So you're moving the 0 point over pi over 8. You're also moving the asymptotes over at pi over 8. So what's pi over 4 plus pi over 8? That should be a minus, sorry. That would be 3 pi over 8, right? So the asymptote for this would be 3 pi over 8. So what would be minus pi over 4 plus pi over 8? When you add those together, you get minus pi over 8. So basically what you do here is that would be the other green asymptote, minus pi over 8. Again, the 0 point is pi over 8, so it would go up like that and down like that. So that's really what we're looking for in this concept of sketching a tan function. Where are the asymptotes? What is the period? Where does it start? And that's where the phase shift comes in. And again, we're not going to worry about the amplitude in this case. So cotangent is exactly the same thing, except if you remember, get cotangent of x is cosines on the top, right? And sines on the bottom. So it looks very similar graphs-wise, except the asymptotes now occur when sine equals 0. So that would be 0 pi minus pi, etc. And so if you took a look, excuse me, at the cotangent function, it would look something like this. So you can see it's, oops, that's the tangent. There we go. So you can see it looks very similar to what the tangent looked like, except our asymptotes are different. Same period, right? Here the period again is pi. And you can see that it goes in a little bit different direction where we blew up to positive infinity, but tangent when it goes to the right. Well, since we flipped the fraction, it's opposite, right? Now we're going down to negative infinity. And then when we go to the left, we go up to positive infinity. So that ends the lecture on tangent. I'm going to do another recorded lecture to talk about secant and cosecant.